In this presentation, we are going to calculate energy released per fission. What is energy released per fission? When one uranium atom or nucleus is split into fission fragments, some amount of energy is released at the end of the reaction. Are you clear? Let us take uranium. That when uranium is bombarded with a neutron, that uranium is split into barium and krypton. So before the production of barium and krypton, one intermediate unstable nucleus is created, that is nothing but 92 uranium 236. After the splitting, barium and krypton will be created, and then apart from barium and krypton fission fragments, here 3 neutrons are also emitted in the reaction. They are produced in the reaction. Are you clear? And then look at the final factor called Q. What is Q? Q is called energy released per fission. So this is the thing which we are going to calculate. Are you clear? So how to calculate this energy released in single fission process? Here, this uranium and neutron both are called as reactants. Are you clear? Both are going to participate in the nuclear fission reaction. This 92 uranium 235 is going to be split. And then barium, krypton and 3 neutrons, all the 3 can be combinedly called as products. Calculate the mass of the product and calculate the mass of the reactant, and you have to compare both. After comparing, you could find that mass of the product will be lesser than the mass of the reactant. So we'll calculate the mass of the reactant and mass of the product. Finally, we'll find the difference. So how to start with? Here, mass of the uranium atom to be calculated. Mass of the uranium atom must be known, and you can refer it from log book. Are you clear? Mass of the 92 uranium 235, how much? Its value is already given in the textbook. You can write it here, 235.05045 atomic mass unit can be written as U. And then this is bombarded with neutron, no? Mass of the neutron is equal to, we are supposed to know this value, 1.0086665 atomic mass unit. Now both the two are both have to be added. Are you clear? Both of them must be added. After adding, you will get the mass of the reactants. The answer is 236.054398 atomic mass unit. So this value is called mass of the reactant. Are you clear? Mass of the reactant, and it can be written as MR, mass of the reactant. I will write it everything in short form due to lack of space. Are you clear? So mass of the reactant calculation is over. I am going to draw one segregation line here. Only then the understanding that could be done. Understanding is easy. So I have drawn a segregation line. Now we are going to concentrate on the products. Who are all products? Barium, krypton, 3 neutrons. I will give the subtitle here, mass of the products to be calculated. Mass of the products. First, let us take barium. Mass of which element? Fission fragment. Mass of 56, barium 141. Its mass is also available from the log book, 140.9177 atomic mass unit. And then mass of another fission fragment. Who is that? Krypton 36, krypton 92 is equal to 91.8854 atomic mass unit. And then mass of 3 neutrons. Mass of 3 neutrons to be calculated. Here mass of 1 neutron is mentioned, 1.00866. you know, this one must be multiplied with 3. After multiplication, straight away I will write the value 3.0259995 u can be written. For addition purpose, I will write 0, extra 0 here. Now all the products and their respective masses are written. Now your duty is to add everything. After adding, you will be getting 235.829095 atomic mass unit. This is nothing but mass of the products. So mass of the reactant is calculated, mass of the product is calculated. Now we have to compare mass of the product and mass of the reactant. Look at here. After comparing, it is found that mass of the product is, look at the value, mass of the product and mass of the reactant, whose mass is greater and whose mass is lesser. Now you can easily say, so clear, mass of the product is less and mass of the reactant is more. This conclusion is very important. Mass of the product is lesser than mass of the reactant. So there is a difference in mass. The difference in mass between these two is called, what is this? Mass defect. This is called as, what is this? Mass defect. It is represented by the letter del m. So how to write this? Mass of the reactant minus mass of the product. So in that format we have to write. Now I am going to substitute both the two values here. 236.054398 atomic mass unit minus this one 235.829095 atomic mass unit. Subtract. Though it is given in the textbook, our duty is to rework and we have to work it out. Only then we can understand the problems. Don't simply leave it as that everything is given in the textbook. Our duty is to learn. 0.2253. We have to check it up. Are you clear? We have to learn, no? Are you clear? This is called mass defect. And this much amount of mass disappears. Are you clear? After the fission process. That's why this is called as mass defect. This mass defect, clear, will be converted into the release of energy. This much amount of mass defect is converted into the energy release in the process. Are you clear? So already we have learnt, clear, the basic fundamental formulas are there. The energy released can be calculated by certain fundamental formulas. How to get this? If one atomic mass unit, one atomic mass unit mass is converted into energy, this is in mass form. If this much amount of mass is converted into energy, how much amount of energy you will get? 931 million electron volt. Here, this much amount of mass is disappeared here. So this mass defect to be converted into energy. How to calculate energy released? Energy. This conversion must be known. Energy released in fission process. Energy released in fission process. Okay, energy released per fission. Energy released in per fission process. Okay, that is very important. In this single fission process, how much amount of energy is released? Del m, mass defect, must be in atomic mass unit. That must be straight away multiplied with 931 million electron volt. Substitute 0. And then 225.303 into 931 million electron volt. If it is multiplied, you will get the answer as how much? 200 million electron volt. 200 million electron volt amount of energy is released here. So here we can substitute it now. Are you clear? Now I am going to highlight the value of Q as how much? 200 million electron volt. 200 million electron volt. This much amount of energy is released. Are you clear? Don't forget, this is the energy released in fission process. Are you clear? 200 million electron volt amount of energy is released in each fission process. Don't forget the value. This one may be asked in examination. When one single uranium atom or nucleus is split into these fission fragments, clear, that is called one fission process. In each fission process, how much amount of energy will be released? 200 million electron volt. Here I have highlighted. Okay, thank you.